Hey everybody, this is Larry. This is me going for Q3 of the weekly contest for 9 shortest distance after road addition queries 2. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this one. So this one is actually very similar to Q2, but there are two major differences. One is that N is really big, right? So you can't do anything too sloppy, and this, or at least obviously you can't do the same thing because otherwise that's just Q2. And then the second part is that there's this line that is new, that does not exist in Q2, which is, and they should tell you that honestly. Like, it's just kind of weird that there's all these things, but there's this line, and if you read it correctly, which is kind of hard to read honestly, but if you read it correctly, it just means that there's no crisscrossing of any of these lines. There's no crisscrossing, right? Yeah, and by crisscrossing I mean, let me bring up the drawing thing. That means that there's no crisscrossing, which means, if you are trying to go from I'm skipping the notes in the middle. There are no cases in which this happens, right? That means that all the things, it's just going to be here and maybe here to here, but that's fine. So yeah, and there's no overlaps. So the way that I thought about this problem, and it took me a while for this one, is that well, because you cannot because there's no crisscrossing. If you create an edge, let's say this one that we already created, let's say you created this one, right? This is a query. That means that everything in between is no good, right? Because, well, yeah, that means that everything in between is no good because there's no way, there's no thing that goes to a further thing that you have to make a decision on. You know that here to get to here, this is always going to be the best move. Of course, that's not always true in the sense that, like, if you go here, there are multiple paths still, right? You could go here. Let me change the color real quick. You could go here, or you can say go here, here, and then here in 2 moves. But that's the general idea, right? And the idea here is that, yeah, you just kind of keep on compressing this, and when you have the green one, you could compress everything here. So that's basically the idea. So that now you basically have just one move to here and then here, and this is 2 moves because you could compress the thing. And there are a couple of ways you can think about compressing. You can think about it as deleting the elements in between, and if you delete all the elements in between, then now all the nodes that you have is going to be it's just the number of nodes that you have, because the number of nodes that you have will be from 0 to 1, right? So that's really basically the idea. Yeah, so that's really basically the idea, another way to think about it. So there are a couple of ways to implement this. The way that I did it is with union find. And it's not a trivial union find, just to be clear, because I don't know, you could watch the live portion to see how I did it. And I think I actually did this pretty quick, pretty okay. But the idea here is just able to delete nodes, right? So you have something like this, and then let's say you add a query like this, then now you have to get rid of this node. And the way that I get rid of this node is just by unioning here with this one, so that now this is one big union, right? Okay, let's change this a little bit more, just more clear. But let's say you're skipping 2, then now we're getting rid of this, and we get rid of it by unioning this with this. So then now you have one big node, if you want to count it that way. So then now, of course, the distance is now 3 because now you have 3 nodes, right? So that's really the crux of the idea, and the implementation is a little bit tricky, but it's doable. There are also edge cases, like if now you go, if there's a query from here to here, well, you kind of do the root thing, then you know that this goes to here and this goes to here, so then you don't have to do anything, right? And then there's the other thing of, okay, let's say now let me just draw a new one actually. Let's say you have a lot of edges. Let's say you did this, so then now you got rid of this, and then later you do this. What you want to do is get rid of, say, this node, and this node, but you don't want to redo this node, right? Because if you do it this way, then it's very easy to construct an n square counter case, right? A counter case of that could be very simple, which is just, one node. So you delete 1, and then here deletes 2, here deletes 3, here deletes 4, here deletes 5, ... and it becomes n square, right? So you want to basically set the structure in a way such that you only you only union stuff that is next to, that is not, that is still live and not crossed out. And the way that I did it is by taking advantage of the fact that everything is adjacent and stuff. So then now I keep track of the size of the component, right? And if I keep track of the size of the component, so here, if the size of the component is 1, that means that the next one I have to check is 2. So then now I merge them. And then here, that means that the next size of the thing is going to be, well, what is the next size of the thing, right? Next size. Because let's say this was already previously done. So this component is actually size 2. So then now, when we merge this one, we check this one to this one and we merge. So then now we merge to now a size 4. Then now the next node is going to be one after that, right? And so forth. And that's really the idea that I did. It's kind of tricky and to figure out and prove, but that is really the idea, right? So yeah, so now this is a very straightforward union find. You could watch me solve this live, and it took me a while to come up with it, but as soon as I come up with it, like I type all of this live, remember that A is less than B. So yeah, this is union find with path compression. Looks pretty straightforward. This is union find, and here we always compress to the left intentionally and set the parents to right? And then yeah, and then here, that's basically it. So when you have A, one more thing is that when I add components, and this is how I thought about it. I didn't talk about this explicitly, but when I go from A to B, I actually I'm deleting all the nodes not including B, right? So that means that if you want to phrase it another way, that means that I want to union up to B minus 1. So that's basically the idea here, is that I'm up to B, but basically here we find the root. I did miss this for 5 penalty points or whatever, penalty minutes, because basically there's a case where if this is not the union, or if this is not the root, then you have this case where sorry, hang on. So that's just for if you have this case where it goes. Well, let's the bigger one first. So this one first. So then now here, we already deleted this node. So then I didn't check it. And this node is already complete. Then we know that the right side cannot crisscross anyway, right? Or like cannot cross, because that's by definition. So that means that everything to the right is either going to be deleted or it's exactly the same place. So that means that we can just literally skip it, which is what I did here. And that's why this looks this way, because if it's not, then we can skip it and we just end distance. Otherwise, we do this thing where we check UA plus S, which is the size, and keep in mind that we don't update UA, right? It's UA plus S. We union it, and then the distance shrinks by 1 because we removed 1 node. Remember that even though the second node that you remove may be a super node, it could be a big node of union, right, of like size, say 10, but it's still, we move 1 at a time, right? So that's why we subtract the distance from 1, and then we update the size as to the new size after the union. And then, yeah. And that's pretty much it. And then we just update, after we finish doing this update, we get up to B, then we just append the distance, and that's pretty much it. So what's the complexity here, right? So this is very tricky to kind of analyze initially, right? But the key idea is just that on the right side of this, every node is only going to be unioned once, right? Because by definition, it's a hard proof, but hopefully if you've been following, it's a hard to articulate proof. I don't think the proof is that hard. But hopefully, from what I've said, just to kind of follow along, is that every node gets removed once at most. So that means that even there's a while loop, this is O of 1 per node. in total, right? So that means that for each query, it's going to be O of Q for the number of queries, but it's going to be O of Q plus N is the total complexity. Because the N coming from the fact that we only do one union per node on the right side, right? So another way of saying is that each node can be B at most once. So therefore, yeah, I mean, I guess, yeah, and of course, not including the cases where you skip it, but yeah, so it only calls this union once, so that's why this is O of N. Yeah, and in terms of space, this is O of N, as you can see, and O of Q just because that's the size of the output, right? So this is O of Q plus N space. Yeah, and of course, I mean, and here I assume that union find is O of one time in space. I guess technically speaking, if you want to be pedantic, it's not quite that, but I don't know. Take your argument somewhere. I don't know. Not this one. But yeah, that's all I have for this one. Let me know what you think. Thanks for watching. And you could watch me solve it live during the contest. Now. Spend an extra 20 seconds doing this. Okay. Okay. What's the difference again? There are no two queries such that this thing happens. And then there's also a Q4, which no one's got, so let's focus on this one then maybe. This is a disaster. Okay. So now N is big. Okay. Okay. Such that something about this. So there's no intersection. Okay, what does no intersection mean? Means that if there's no intersection, that this crops is going to be 2. I mean, you can't even do N squared, right? There's a lot of queries. So that means that you basically have to do it in log N. The no intersection means that you always want to go to a point in which there's a beginning, right? No intersection. Yeah, so that means that here, and you want to go as far as possible, right? So basically, for each one, you want to go to the next one, and that's the distance. So then it's just the critical points. Not always the next one, it's just the next beginning point. Right? And then just sum it all up. Okay. Huh. No intersection means that. Okay, so now, right, if I have a sec tree, how do I want to do it? Square root decomposition. Can I do square? What's it? 10 to the 5th? 100,000. How would the square root decomposition work? Now you can't do square d squared. That's too slow still because it's on each query. So you have to be faster still. We have an hour. And I was very slow in Q2, so I have to solve this to not lose a lot of weight. It's fine though. But okay. Still no one's gotten it. I'm not gonna even try. But that's maybe because people are trying this one though. Alright, let's take a look real quick. Oh, there's a change thing, so then now you have to I don't know. That seems like people would have gotten it if people are smart. Or like the smart people would have gotten it. Union fine. Because basically we just want to maybe union fine. So now we just combine 2 and 3 and then we just have the number of nodes, and the number of nodes is the thing, right? I think that sounds right. Okay. How do we have to be smart in the unioning though. Okay, yeah. I think I have an idea, but also need size, which is how far it extends. Oops, nope. Because it never overlaps. Okay, fine. Oops, where am I writing it? We want the root to always be the smaller one. Yeah, why not? I think it should be okay. And A is always going to be less than B, I think. So then now we want the parent of UB is equal to UA. And then the size of UA, size of UB. Okay. And then now, yeah, okay, for so then now maybe we start with distance is equal to n, right? Yeah. Oh, n minus 1, I guess, is the shortest path always in the beginning. But you can't use this on the other one because this intersection thing doesn't exist, right? So, okay, then now we want to say okay, size of oops, that's terrible. Okay, so then that means that yeah, we start from So if the size is 1, then we do a plus size minus 1. No. A plus size, we want to do from a plus size to from this to b minus, or not including b. So okay. I think this is right, but it has to do, you have to do some skipping. Alright, so okay, fine. While a this should always be true, actually, because of the no overlapping. If not, then I'm a little bit weird. Yeah, that should always be true. Is less than b, because we want to combine it to b minus 1, right? Then we want to union a, and also a plus s. But then now we have to count the number of distinct components. So okay, so that means that okay. Okay. Right. But this means that one thing has been removed, so distance 1, right? In theory. I need in both places. It's more like a do while. 3, 2, 1, 1, 1. YOLO submit. Okay, so this is wrong. I mean, I don't think I have any idea anyway, so it's fine to have a wrong answer on this one. But okay, 1, 4, and then 2, 4. Oh, because then now it merges. Okay, so if it's okay, so if this is not the case, then we just continue. Oh well. Because we already merged it with either B, or it cannot go further, right? What's the answer for this one? Is it just 2, 2? 0? Yeah, probably. Is it? Is that right? Because it's 0 to 1 to 4. Oh, 4 is the last number. Okay, fine. Yeah, okay. So maybe I didn't need that. YOLO. Okay. Whew. No, I guess, I mean, I did. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this contest, everything in between, this explanation. I don't know. Stay good, stay healthy, do good mental health. I'll see y'all later and take care. Bye-bye.